In today's video, I'll talk about fermion and boson, and then the next concept that I should be able to talk about is the set theory. So first, talking about the fermion and bosons, they describe the symmetrical and anti-symmetrical state of a matter, which is important in proving other theories in quantum mechanics. So first, the fermion equation that was made by Enrico Fermi and Paul Dirac is 1 over E epsilon minus mu k slash k b t plus 1. This is the equation for the fermion, and the boson, which is the orange part of the graph, which you can draw, like, for example, if we draw the graph, there is L over 2 and another L over 2. L and L, this part and this part will be made. So the first part will be made with a fermion. The second part will be made with a boson. Then another part. This is made like this, and another part, this part will be boson, fermion, and boson, and fermion. This is one part of the probabilities, and since there's fermion here, the other part should be fermion, and the adjacent part should be a fermion or a boson, because this part is a boson, and if this is a boson, then this should be a fermion, and if this is a fermion, this should be a boson. So this is a fermion or a boson. L represents the potential energy of the fermion and boson's product. So this is an anti-symmetric graph. So there is a boson here, and the adjacent side there should be fermion. The other adjacent side there should be a fermion, but then there's a fermion here, so it should be a boson. So it's a boson or a fermion. There is a clear difference between a fermion and a boson or a fermion. And then there's the symmetric. Symmetric is basically meaning the totally same thing. If this could be a fermion or a boson, this could be a fermion or a boson. This is not the same thing, so this would be a boson or a fermion, and a fermion or a boson. This one is a fermion or a boson, fermion or a boson. Symmetrical is almost the same thing, and both of the L are having the same potential energy. This one has different potential energy. This is the formula for the fermion, and the fermion equation has the degree of n to the f, which is fermion, that should be smaller or equal to 1. If you move next to boson, which is bosons they are 4 atoms: axiom, photons, and boson. E epsilon minus mu slash k b t minus 1. The reason why this could be minus 1 is because it's not bound to epsilon going to mu. The variable are, so the epsilon I have put in here is the energy state. There's the mu, which I put it as the chemical potential. And then there's also this, representing B is Boltzmann constant. Boltzmann constant is a constant that is made from Boltzmann, and then he made this to represent the value of different fermion and a boson. As you can see, we put K and B here, but then this time we put it as T, which is time, and this one is absolute temperature, which I'm going to write here. T is absolute temperature, K to B is Boltzmann constant, mu is chemical potential, and epsilon is energy state. There's anti-symmetrical and symmetrical, and there's also nothing. No symmetrical. Non-symmetric. Non-symmetric can be represented like this. So this goes right over the quarter of this fermion. The middle will be always the fermion or the boson. But then the upper part is a fermion and the smaller part is a boson. This one should be fermion or a boson, fermion or a boson, and boson. Fermion or boson, boson or fermion or boson. As you can see, I wrote, this is a fermion and the opposite adjacent corner is a boson, which is the opposite side. For a fermion, there is electrical charges like electron and different atoms. This was concept about fermion and bosons, and I'll now talk about the set theory. The set theory is a theory that it proves, with the set, it proves different, if we substitute in different values, like for example, energy state, inside here, we get Rho, psi, and phi, like this. This is the set theory, and there, for example, if we put mu, which is the chemical potential, if you put it in, will be E epsilon, which was one of them, so we can put psi because it's the wave function, minus mu, which we put it as E epsilon, and psi, phi. And then for the Boltzmann constant, which I'm not sure about, is Boltzmann constant if we substitute in here, which will be K, F, or B, and B, comma, wave function, if we substitute in wave function 1, F, comma, B, and phi. Absolute temperature, if we substitute in here, T, epsilon, which was phi, E phi minus E phi to the power of E phi, slash this one, phi 1 F B. Phi was T minus phi 1 phi comma F comma B 1 K and then T comma psi. Now I'm gonna do it for every single one because the set theory puts in the values and it makes the values possible to get in every equation. For example, when I put the energy state, there's only one epsilon, and we should make all of this epsilon, which will be substituting. And to know all of them, we needed all of these four. That's why I wrote them down. We need all this information to find one epsilon, which would be in a form of pho. So I'll number this as 1, 2, 3, 4, with number 1 first. Number 1 is epsilon, the base value. Pho, if we put it in, will be epsilon E phi minus pho psi, wave function, comma, psi will be E and then K, KBT, which was, KBT was here, T minus psi, comma, FB. See, we're putting everything as epsilon in the base. Then phi will be E and phi, because it's just 0. See, right now I put everything as epsilon, which will be able for us to put in, which will give us a number. Right here, this will be a number, some kind of number that we don't know. And then we plus 1, and then we divide it. Yeah, we put it as a fraction. Number 2, mu, and then base will be mu. Put it in E mu minus actually we can put this as KBT. This one too. I think we can put this at all of them as KBT, comma, mu bar T minus mu, comma, mu to the power phi. Like this. Number 3, this one is a hard one, K to B. And this one is hard one, so I've already put this in. We get this one, which is not the value we want yet, but then we should first put in this, the later solvant, comma, K, B, F slash B, comma, K, be phi. Like this. Number 3 again, because we haven't got the value yet. Only one left. KB, K, and B, F, K, D, T over D, and then so on. Number 4 is already made, only to vary this one. And the reason why there's psi in here is because we can replace this with phi anytime that we want to. And then we put this in because the wave function is added to this one, which will make it disappear. So you gotta plus wave function to everything in there. F, comma B, comma. Since we have a wave function here, if we add a wave function 1 actually, psi 1, phi comma phi f, we'll put this up, e, psi comma f slash b k t dt over d and phi 1 plus phi 1 comma t to the power of phi. As I did here, we can make everything to the base of the set like this. In this video, I talked about Fermion and Boson, which represent electrical charges in the particles which we can identify in later findings. For example, in NASA, they can find aliens with these two things. And then we talked about variables, graphs of fermions and bosons to better understand the concept. We talked about the set theory, which helps us substitute every value into the fermion and boson equation. Like this, we put all the base to the equal points. And by knowing this, we know this, which gets a better concept of both things, so that we could understand better. Thank you.